Have you ever wondered about the color of stars, or why objects glow when heated? These phenomena are linked to a fascinating concept called blackbody radiation. It's a fundamental idea in physics, explaining how energy interacts with matter at a fundamental level. The story of blackbody radiation is a journey through the history of physics, full of unexpected twists and profound implications. It's a story about how we came to understand the universe in a whole new light. Blackbody radiation is the electromagnetic radiation emitted by an object in thermal equilibrium. This radiation spans a range of wavelengths, creating a characteristic spectrum. Understanding this spectrum was a major challenge for physicists in the late 19th and early 20th centuries. The quest to understand blackbody radiation led to a revolution in physics. It ultimately gave birth to quantum mechanics, one of the most successful scientific theories ever developed. This theory reshaped our understanding of the universe at the smallest scales. Join me as we explore the mystery of blackbody radiation. We'll trace the steps of the brilliant minds who unraveled its secrets. We'll see how their discoveries shattered old paradigms and paved the way for a new era of scientific understanding. Before we dive into blackbody radiation, we need to understand the scientific landscape of the late 19th century. Physicists were grappling with a fundamental question about the nature of light. At the time, light was thought to be a wave. But waves, unlike particles, need a medium to travel through. Think of sound waves traveling through air or ripples moving across water. Scientists hypothesized that light waves traveled through a medium called the luminiferous ether. This ether was thought to permeate all of space. It was a comforting idea, as it fit with the classical understanding of physics. In 1887, Albert Michelson and Edward Morley set out to detect this elusive ether. Their experiment was ingenious in its simplicity. They reasoned that if the Earth was moving through the ether, the speed of light should be different in different directions. Their experiment, however, yielded a shocking result. They found no evidence of the ether. The speed of light was constant, regardless of the direction of measurement. This unexpected outcome sent shockwaves through the scientific community. Now let's turn our attention to the heart of our story: blackbodies. Imagine a hypothetical object, a perfect absorber of radiation. This object would absorb all incoming light regardless of its wavelength or angle. No light would be reflected or transmitted. This ideal absorber is what we call a blackbody. Of course, no real object is perfectly black, but we can approximate a blackbody in the lab. Imagine a cavity with a small hole. Any light entering the hole is unlikely to escape, as it will bounce around inside the cavity and be absorbed. This setup behaves very much like an ideal blackbody. Here's the fascinating part. When a blackbody absorbs energy, it also emits radiation. This emitted radiation, known as blackbody radiation, has a very specific spectrum. The spectrum depends only on the temperature of the blackbody. Think of a blacksmith heating a piece of iron. As the iron heats up, it starts to glow. First it emits a dull red, then a brighter orange, and finally a brilliant white. This change in color reflects a shift in the emitted radiation spectrum. The hotter the object, the shorter the peak wavelength of the emitted radiation. The study of blackbody radiation began in the 19th century, a time when scientists were fascinated by the relationship between heat and light. Pioneers like Samuel Langley and Gustav Kirchhoff made significant contributions to the field. They laid the groundwork for understanding the properties of blackbodies and their emitted radiation. Langley, an American astronomer and physicist, developed highly sensitive instruments to measure infrared radiation. His work was crucial in understanding the energy distribution of sunlight. Kirchhoff, a German physicist, formulated the law of thermal radiation, which states that the emissivity of a body at a given temperature is equal to its absorptivity at that temperature. In simpler terms, good absorbers of radiation are also good emitters. Then came the contributions of Joseph Stephan and Ludwig Boltzmann. Stephan, an Austrian physicist, empirically discovered that the total energy radiated per unit surface area of a blackbody is proportional to the fourth power of its absolute temperature. This groundbreaking finding, later theoretically derived by Boltzmann, is now known as the Stephan-Boltzmann law. It elegantly relates the temperature of a blackbody to the total energy it radiates. These early investigations into blackbody radiation set the stage for a deeper understanding of the phenomenon. Scientists were beginning to unravel the intricate connection between heat, light, and matter. In the late 19th century, German physicist Wilhelm Wien made a significant breakthrough in understanding the blackbody radiation spectrum. He focused on the relationship between the peak wavelength of the emitted radiation and the temperature of the blackbody. Wien's law, as it came to be known, stated that the wavelength at which the intensity of the radiation is maximum is inversely proportional to the absolute temperature of the blackbody. Think of our blacksmith again. Wien's law explains why the iron glows red at lower temperatures and transitions to white as it gets hotter. The peak wavelength of the emitted radiation shifts to shorter wavelengths, towards the blue end of the spectrum, as the temperature increases. Wien's law was a remarkable achievement. It accurately predicted the behavior of blackbody radiation at shorter wavelengths. It provided a mathematical framework for understanding the relationship between temperature and the color of a glowing object. This success earned Wien the Nobel Prize in Physics in 1911. However, as we'll soon see, Wien's law was only part of the story. It worked well for shorter wavelengths but failed to explain the observed spectrum at longer wavelengths. The mystery of blackbody radiation was far from solved.
If you enjoy this channel, don't forget to hit that follow button. Your support drives my creativity, and together, we explore the wonders of science. Let's make discoveries together.